Whether you are a renowned astronomer or a distracted observer looking up at the sky at night, you'll be enchanted by the brightness of the stars. As a distracted observer, everything stops there. You need to return to your normal activities. The astronomer, however, wants to go further. Behind his telescope, what use does he have of making considerations about the stars and galaxies they form? The answer is only one: light and all other forms of electromagnetic radiation. He believes light travels in a vacuum with fixed and limited velocity, so he looks at stars with the appearance they had in the past. Desperation knocks at the astronomer's door. He needs to know what happens in distances that cannot be overcome physically, and the only source of information he has comes to him with immense delay. Until, in 1842, the work of the Austrian physicist Christian Doppler appears. Doppler studied sound waves, demonstrating that a moving source would affect the frequency of the waves, timbre, if they were received by a fixed observer and outside the system. The French physicist Antoine Hippolyte-Fizeau (1819–1896) decided to extend the effect of sound waves to light, considering that, for classical physics, light would propagate in the form of continuous waves. Although this was later questioned by Planck's ideas with the oscillators and Einstein's theory of the photoelectric effect, astronomers refused to give up the only source of data they had on the distant universe. They continue to believe, still today, that the light of a distant star would cross the emptiness of space in the form of a wave, and without any solution of continuity. If the waves emitted in the Big Bang were continuous, it would be so if you followed them in the direction of the singularity, or in the opposite direction. It is true that 50% of the path traveled by cosmic radiation, that is, from the Big Bang to our days, could only be evaluated indirectly. That is, who gives us the measure of time that separates us from the uniqueness, is the light that would already be found in our past, and this would be done by a form of remote tracking. Therefore, the light used is considered to be a cosmic background radiation. If the light waves were continuous, still, we could artificially shift the beginning of the time counting. That is, although the beginning of time is always in our position, as isolated observers that we are, it could be moved to the position of any star. In the case of center next star, landmark 0 would be shifted to 4.3 light-years away. Planck argued for the classical wave theory, and the concept that light, although quantized, behaved as if it were a wave, when moving in a vacuum. This, even though he was revolutionary in demonstrating, in his experiments with electromagnetic oscillators, that the light would be discontinuous. He demonstrated that atoms would behave as small electromagnetic oscillators, each one with a characteristic frequency of oscillation. That is, the energy of the oscillators would be quantized. Oscillators do not radiate energy continuously, but only by means of pulses or quanta, which are multiples of the quantum. When the quanta are emitted, the oscillator changes to another quantized state. The hydrogen atom, for example, only exists in certain so-called stationary states, during which it radiates nothing. An oscillator does not emit or absorb energy while it remains in one of its quantized or stationary states. It only emits energy when changes state. Despite quantizing the energy of the oscillators, Planck continued to treat the radiation inside the cavity as if it were an electromagnetic wave. Einstein, in 1905, applied the concept of energy quantization to a new area of physics, the photoelectric effect. The classical wave theory could no longer explain certain effects. It predicted that the kinetic energy of photoelectrons increases as the light beam becomes more intense. The photoelectric effect has made it evident that energy is independent of the intensity of light. It is from the classical wave theory that the photoelectric effect should occur at any frequency of incident light, provided that it is sufficiently intense. However, there is a cutoff frequency. For frequencies smaller than this, the photoelectric effect disappears completely, regardless of the intensity of the illumination. The fundamental point of the classical wave theory, put in check by the photoelectric effect, is related to time. It says, if the light were less intense, there should be a measurable time lapse between the moment the light strikes the metal surface and the ejection of the free electron. The electron should be, at this time, sucking energy from the light beam until it accumulates enough to escape the metal. However, it has not been possible to measure any time interval between the incidence of light and the ejection of the free electron. When a quantum strikes an electron, both appear simultaneously, both Geiger 1928. This detail is fundamental to the observer because, in fact, he does not see the particle directly, but the light scattered through it. The absence of measurable time between the incidence of light and the ejection of the photon would affect his point of view. The observer looks at the sky at night and sees the source of light, as in the case of a star, instantaneously, without depend on the time the light would have taken to move in a vacuum. The most classic example is that of an observer using a microscope to analyze a blade with stained cells, and another observer using a telescope to observe the moon. Both depend on the local scattering of light quantity, which would totally exclude the time that could be separating the observer from the observed object. Einstein concluded, based on the photoelectric effect, that the energy of the light beam travels the space concentrated in packets, called photons. In the case of a star, Planck believed that light, although emitted by the source discontinuously, propagated in the vacuum like an electromagnetic wave. Einstein suggested that light, as it traverses space, behaves not as a wave but as a particle. This shocked the scientific community at the time, as it hit the Doppler effect in full, throwing a blade of flame over it. The observer's dependence on the local scattering of light quantity could explain the instantaneous observation of the night sky as the product of a translation of information encoded in light. In spite of the immense delay suggested by the speed with which the light would cross the vacuum, there is no news of the existence of an earlier time destined to this translation. It is as if the light was always at our entire disposal, to be followed only in the direction of our past. The future does not exist for us, for we would be totally dependent on our memory. One cannot think that our consciousness could act in a discontinuous way, as suggested by the photoelectric effect, simply because nothing exists outside this consciousness. This would explain the concept of continuous waves, but it would be restricted to the time in the past. It is our memory that would sustain the concept of continuous waves, and this became part of our physical reality. Doppler and the velocity of light would be part of this package. With that, time would be a form of exile to which we would be subjected, which suggests that time would be contained in the isolated observer himself, by exclusion of direct access to the future. For example, the time of 13.7 billion years, which light would have spent after the Big Bang to reach us in the present, would result from an indirect form of evaluation, and when that time could be measured, it would already be considered a thing of the past. The observer depends on the local scattering of light emitted by a distant star to know its existence. Before the light reaches Earth, the star does not exist, although it is there. This light must first be quantized to become apt to be perceived by our senses. All forms of energy that allow its measurement are quantized. As Planck has shown in his experiments with electromagnetic oscillators, there is no irradiation or energy absorption in the quantization phase. That is, there would be no measurable waves while the oscillator remained in one of its quantized states, hence called stationary. This dependence of the observer on the wave nature, predicted in the scattering of light after a previous packaging phase, would be a curious alternative to explain Einstein's assertion that, by traversing the vacuum, light could only use its particle-like appearance. In addition, if the corpuscle aspect of light exists only in the steady state of the particles, it is explained why a particle cannot be observed in real time. In other words, what we see is the light scattered by the particle and not itself. The waves, somehow, disturb the particles, generating uncertainty in their position or velocity.